and welcome to today's live broadcast of Basic Principles of Laser Induced Breakdown Spectroscopy. We're delighted to bring you this educational web-based event presented by Spectroscopy and sponsored by Andor Technology. Andor Technology has over 20 years' experience in the manufacture of high-performance modular spectroscopy systems, offering the latest in cutting-edge technology in the fields of sensors, electronics, optics, vacuum technology, and software. Andor's high-performance modular spectroscopy solutions feature a combination of market-leading, highly sensitive detectors and pre-aligned, pre-calibrated spectral instruments. And with over 10,000 Andor users in 55 countries, Andor products assist leading researchers in achieving high-quality results and breakthrough discoveries through techniques such as microspectroscopy, Raman, LIBS, or fluorescence spectroscopy down to single photon. We have a few important announcements before we begin. This webcast is designed to be informative, and we encourage you to ask questions during the event. You can type your questions in the Submit Questions box located below the presentation window. Due to the large number of participants, we may be unable to answer your questions live. You can enlarge the slide window at any time by clicking on the Enlarge Slides button located below the presentation window. The slides will advance automatically throughout the event. If you're experiencing technical problems with viewing or hearing this product, please click on the Help button below the presentation window. I'm Dave Walsh, Editor-in-Chief of Spectroscopy, and your moderator for today's event. We're very pleased and honored to be joined today by Mathieu Baudelet. Mathieu received the BS in Physics from the University of Lille, France in 2003 and began his work in spectroscopy with Fourier transform microwave spectroscopy. In 2005, he received the MS in Laser and Spectroscopy from the University of Lyon, France, working on theoretical quantum optics. Then, in the Laboratoire des Spectrométrie Ionique et Moléculaire in La Cime, Lyon, he completed his PhD in laser-induced plasma and spectroscopic analysis under the direction of Professor Jin Yu, showing the advantages of LIBS for biological sensing and food monitoring. He has written for many publications on the use of femtosecond pulses to improve this technique and the development of analytical techniques to understand and extract the maximum information from the LIBS spectrum of bacteria. He is now continuing his research on laser spectroscopy and sensing as a senior research scientist for the Towns Laser Institute at the University of Central Florida, Orlando. His panel covers the fundamentals of laser-induced plasmas and the application of laser spectroscopies such as LIBS, Raman, and FTIR as fundamental diagnostics as well as sensing techniques for defense and environmental applications, and the study of propagation of ultra-short laser pulses for sensing purposes at distances up to the kilometer range. Thanks for joining us today, Mathieu.
Hi, thanks, Dave, for this introduction, and thank you for letting me this opportunity to present this seminar on the basic principle of LIBS. And so first, and I want to thank the audience, and I want to be sure that people understand like the real meaning of and the real goal of this presentation. On this slide, and I entitled "What is LIBS?" It's really to make the difference between LIBS and the physical aspect of it. So LIBS by itself would be the analytical technique. So you can have this idea if you have a LIBS instrument itself would just be one step in the process. If you want to know your sample, and this instrument is just here to give you data, and then you analyze those data, and then you go in your decision process. And if you open this box, then you see that you have different components. And those components, for sure, like you can see in the name of LIBS, is you get the laser to induce this plasma from your sample. Then you get this plasma emission, and this emission will be analyzed and to provide you the data for the rest of the process. And on this seminar, I want to focus on the basic principles, so I won't go on very technical aspects, but mainly on the phenomenon itself, that is the laser-induced plasma or the breakdown, and how to use this phenomenon to obtain the information from the sample. So as you can see on this slide, I will focus on how you can get plasma from any sample, and what is the kind of emission you expect from such a plasma. And why going back to those basics is because LIBS is very unique in a sense that you can create very optimized tools to address a problem. And the only way, as any analytical technique, is to understand the basics if you want to apply it very efficiently. So first, a very short overview. I didn't want to go towards the 50 years or kind of the LIBS, but I wanted to show the very beginning of it. And so we can go back to 1860, I would say, and you get the paper by Kirchhoff and Bunsen, and showing the use of this controlled flame for analytical purposes, and even some elements have been very well intense studies with this flame. And then 50 years ago, and this is a nice anniversary this year, the first laser built by Maiman, and that was kind of the revolution. And then the idea came very shortly in '62, and why don't you use these lasers to create this flame or create this plasma by extracting the matter and then exciting the matter you just extracted. And this is this paper and by Bresch and Cross that was during this 6th International Conference Spectroscopy in the US. And then a year after, there was this very nice paper by Mrs. Debras, Guedon, and Liodek, who presented a kind of an overview of several samples. And thanks to this study, we can see that there are some very nice LIBS opportunities that they already saw at this time. And I think I want to talk about this third paper by Archbold on the time resolved LIBS. And this you can see on the bottom right this short time resolved spectrum of a laser induced plasma. And that shows that you have this continuum at the very beginning, and that was kind of the notion of why time resolution is very important in LIBS. And I think those three papers were the very beginning because they were addressing the basics, and they were addressing the technical difficulties that you have to deal with in LIBS. But who is the community, I would say, for LIBS? Now you have more than 50 countries doing research in LIBS. You can see them in yellow on this map. Mainly every continent has its a LIBS lab, I would say, and analyzing many different samples having different purposes. And there was this community addresses either research on the modeling part, on the development part, and this development part is very intense when you go towards the industry. And here is just an overview of some companies, mainly based here in the U.S., some European ones, doing either very compact systems for application in the field, or having benchtop systems, very specialized, like you have here Pharma Laser, who's doing analysis of drugs, for example. You have other, you even have some companies who just deal with analysis of the data, because LIBS is so rich, as many of you know. LIBS as a plasma technique has a very rich spectrum when you analyze the data, your sample. And so you need to have a nice understanding of what is the LIBS spectrum if you want to have a very efficient analysis. So even some companies are specialized in this field. And just 2 weeks ago, there was this international conference in Memphis, Tennessee, in the USA, showing that the LIBS community has a very intense activity. And so you can see across the Atlantic, you have on the both sides, you have the European community, and they have their own conference every 2 years at the same time as the North American community as is. And so I put some dates for some people who would be interested here. Like the sixth one will be in Turkey in 2011, and for the LIBS in North America will be in Clearwater, Florida. And the next international one will be in Cairo, Egypt, for the International LIBS conference. But so this community has a lot of publications as well, and it's been kind of exponential along the years. And but I want to mention quickly where, if you're really interested in understanding basics and applications of LIBS, and follow up what is the state-of-the-art in research. There are 4 monographs, 4 books of LIBS. So there is a very intense community to write those books, and really appreciate those people who you can talk to, and they have a very nice overview of the technique. Then the main journals where you can find the state-of-the-art research, and mainly it's applied spectroscopy, for example, Spectrochimica Acta. JAS has more and more LIBS paper, and we know what's the level of quality in JAS, and it's very nice to see that LIBS begin to be recognized for the quality of this work. And Applied Optics is also a very nice journal where you can find other research activities. But LIBS is not by itself a community. It's very related to other communities, and there are several. There are the very fundamental ones, like the laser material processing. So laser material processing, why? Because as we said, the LIBS is just you need to extract the matter with the laser, and so you want to optimize this. So the laser material processing field is the expert for laser ablation, laser material coupling, laser material interaction, and we learn a lot from them. There is also what I call the plasma-based spectroscopy field, that will be all these very well established techniques like ICP-OES, GD-OES, and even a lot of publications in books, even on flames and sparks spectroscopy. And those techniques are really, really important for LIBS, because this is the same kind of temperatures, the same kind of electronic density for your plasma, so you learn a lot from them. Then on the equipment side, we work a lot with the laser development field, because, as we said, you want to optimize your laser source to address the right questions. So you also want to have compact sources. You want to have adapted pulse durations. You can go from nanosecond to femtosecond usually. And so you need to work in parallel with with the laser development teams. For spectroscopy, so you need your spectrometer for sure, and LIBS is so broad. I would say in emission, you can have a nice emission from the far UV to the IR, and so for this you need to have adapted spectrometers and companies ready to provide those instruments. For the detectors, as you'll see later on, you really need to have detectors that can catch this pulsed event, and this pulsed event can last like a few microseconds. So you need to have fast enough detectors to have an optimized detection. So usually companies, you can work with companies directly working with chips or the electronics, and then we have the ACCD, and then the CMOS technology is something that's going on and growing. There was a nice talk on this LIBS conference showing the advance of the CMOS technology. Then, as I was telling you, some companies are working on data analysis. So we learn a lot from the chemists themselves for their chemometric analysis, the pattern recognition, all these techniques that sometimes are not used in other fields, like in ICP or in GD. But here we use all this information and all those fields. We try to have them around us to develop the best technique. So then, why going back to basics again? And then I start this seminar because there are several steps in a LIBS event. When I say LIBS event is you bring the laser, you extract, you excite the matter, you let it relax, you have a spectrum, and then you have your information. But this, you have many processes you need to understand, and you need to control if you want to optimize your analysis. So laser absorption, for example, for the sampling, plasma formation for the excitation, plasma cooling and emission to optimize the detection. And understanding this will be a great help for going to niches where LIBS can sometimes be the only option. So now let's go on some more fundamental science and explain the first step. That is, I bring my laser on the sample, this laser pulse, and I extract, I sample a bit of it, and I excite it at the same time. So I do a laser evaporation and the plasma formation. Here is just an overview of what would be a linear laser absorption of 3 different kinds of materials. So I put this equation, that is the temperature diffusion in a material, and it's a very well-known equation you can find in many laser material interaction books. And you can see that on the first term on the right side of the equation will be just the diffusion equation, the diffusion term. But then on the right, you will have the source term. In this source, you can see there is the absorption term, alpha, and there is the reflection term, R. And those two terms are really important because it really shows the coupling between your laser pulse and the material. And here are some examples, like for a metal, you can see that you will have for low wavelength, so higher frequencies, you will have a very nice absorption, your low absorption, low reflection. And so the thing you would want to optimize the absorption but lower the reflection. So you have to find this small range if you want to optimize your interaction. Then if you go to non-metals, you begin to have absorption bands, and here is just an example if you have a band gap around this omega naught. And then you can see that you begin to have some features in this absorption spectra. And then you can go to a very complicated case, like here is the tissue interaction, tissue absorption coefficient. And when you have this kind of spectra, you want to detect a specific element, for example, in LIBS, then you can address specifically one absorption band that you know will help you to have the best signal and the best analysis. So the wavelength optimization is a very important parameter in your LIBS analysis. Then the interaction, all those that work. Here I just showed the linear one, but the nonlinear absorption happens if you have lasers in the sub-picosecond regime. Why? Because the sub-picosecond regime leads to have no equilibrium between the electrons you have in your material and the lattice or the matrix of your material. And because of this, you can begin to create nonlinear processes in your sampling, and you can go even shorter and have under 10 femtosecond, and then in this case you even have no equilibrium between the electrons themselves. So you have different processes. You don't play only with the wavelength, but you can play with the pulse duration to optimize the process you want to have, and you can even go with the intensity just to reach those nonlinear processes. And those nonlinear processes will be, you can modify the electronic characteristics of your material to optimize this extraction and this sampling. You can generate more free carriers by multi-photon absorption, impact ionization sometimes, and you can even create lower damages and have still a nice intense plasma. Then, once you have this interaction between the laser and you have extraction of the matter, then you want to have this evaporation. What you want to do is you want to create a vapor, and this vapor will be very important to go towards the plasma. So I'm sorry for these equations. It will be fixed later on. And so the idea, you can go on the left figure, and the idea is when you see these phase diagrams, you want to go from a solid to a vapor. So you need to go, you need to reach first the liquid phase, and then you need to go to the vapor phase. So if we are thinking in linear absorption, then you want to go from a set of parameters like the pressure, the density, and the temperature of a solid. Then you bring this source for this laser. You pass the boundary between the solid and the liquid, for example, and then you have the melting of your material. And then you pass, again, you still bring a lot of energy via your laser, and so you have evaporation of the material when you cross the liquid vapor phase. So all those processes have to be understood, and you can optimize the evaporation of your material for a better signal. So then, once you have the evaporation, what you want to do is not only have a vapor, because your vapor can be a simple gas, and then you will have quasi no signal from the constituent of this gas. So what you want to do is form a plasma. And this plasma formation is one of the big steps, because here you need to have a lot of electrons that will ionize your matter by cascade ionization. And so the first electrons, you have them with the laser, just grab them from the surface. So you have the work function that gives you the first electron by thermodynamic emission. And you even have evaporation during the melting of your material. You have the electrons can be ejected from some dust particles, some aggregates, or some droplets in your plasma. So all those electrons will be of importance, and this is the main thing in your plasma. And sometimes, usually I would say, everybody has a nanosecond laser. I would say in their lab, it's easier to get a nanosecond laser and a femtosecond laser. And then this time scale, the nanosecond, is longer than the plasma creation time. And so the laser brings energy to those photons and to this evaporated matter. So you can have multi-photon ionization with this high intensity and this high electronic density. You have lowering of the ionization potential of your atoms and your ions, so you can create direct ionization as well. So once you have this plasma formation, then you have this equilibrium between ions and electrons. And this equilibrium is governed by the psi equation, and this is the rate. This is the rate constant of this equation. So you have an atom or an ion, and you go to the next stage of ionization, and you deliver an electron. And you can go back with your group combination. And in LIBS, usually you don't go so far in the ionization stage, so you have singly ionized the neutrals, and because the temperature won't be higher than 2 to 3 EVs, that gives you something like less than 35,000 kelvins. And so this plasma formation is the key, and this is the very beginning of your LIBS event. Then, as I was just telling you, you can have the laser itself, usually the tail of your laser, so the front of your laser extracted the matter and created the plasma, but then the tail of your laser can still go in the plasma, and then you can have what is called the inverse Bremsstrahlung. That is, you accelerate your electrons, but already free in the plasma. I mean, you accelerate them with the radiation of your laser pulse. And so that can happen because you have acceleration around neutrals and ions. So these two kind of equations here that you see is really dependent on what kind of radiation is your laser. So you can see it on the first term on each equation when you have this equilibrium, like the Planck equilibrium term, extracting from this equilibrium. And so from this, you have the laser optimization to drive your electrons. And then on the next part of the equation, you can see it's really dependent of the density of your atoms. And that goes back to the optimization of the extraction you're just talking to at the beginning. So here I kind of passed into a review of how you would, very simple review on how you would create a plasma from a solid target. And now once you have this plasma, then it will expand in the background gas around and reach, so with the different processes you have in, reach some kind of equilibrium. And this is a very important notion when you have the LIBS event. So first, this expansion, you have a gas, so you have a vapor, it's ionized, but anyway, what you have is the hydrodynamic of a fluid. So you have the mass conservation, you have the momentum conservation, and you have the energy conservation. So the energy conservation, you have the normal terms that you see if you let this gas expand by itself, but you have those two terms at the end of the third equation. The first one is the laser heating by the inverse Bremsstrahlung, as I was just telling you in the slides before. And you also have the losses. So you have recombination of your electrons, and you have the Bremsstrahlung emission. So all those processes that lead to these radiative losses are mainly governed by the electrons. So you have this electron density around your matter, and this will lead you to elastic collisions. So this won't help so much to get some excited species to get you a signal, but you can get inelastic collisions. So by collision of an ion with an electron, it will excite and go on an excited state. Then you can have ionization itself that can help to have higher states of ionization, and so more signal later on by relaxation. And if you have some radicals, for example, here an example is the radical AB, you can have dissociative attachment that gives you creation of some negative ions for a short time. And you can even have dissociation of this, an equilibrium of dissociation between electrons and those radicals. And those electronic processes are also occurring at the same time with some collisions with atoms and molecules together. And so same thing, you can have elastic collisions, you can have inelastic collisions, and so as we were saying, it's just that you need to have these excited states if you want to have emission from your plasma. You can have ionization, and you can also have associative ionization, and some other processes that are very important, the transfer, so you can excite one with another, that can be used to, in some configuration, to excite a specific species in the plasma. You can have radical formation. So with free body here, you can create those radicals like AB, and chemical reactions themselves. All those processes and those collisions are very important, and I want to focus on the collision term because that leads to the important notion of equilibrium. And the plasma equilibrium, here it's resumed in one slide, but I will spend a bit of time on it. If you have equilibrium, what do you have? It's just you want the equilibrium of the kinetic energy of your species, but you have different species. You have the electrons, you have the ions, you have neutrals, you have radicals, molecules, and all of them, if you want an equilibrium, you want them to have a Maxwell distribution of their velocities. So this is one kind of equilibrium that is important. Another equilibrium is the internal energy distribution on one atom or one ion. So the well-known distribution of the Boltzmann distribution, just to have distribution of your electrons on your energy levels, and this will help you to really have an analytical solution for knowing the composition of your plasma. Then you can have chemical equilibrium. So I put here a very broad equation that A plus B will give you AB. But so that can work for ionization, as we saw with the Sa equilibrium. So an ion A plus B would be the electrons, and so you can go back to the neutral. You can have dissociation and radical formation. So this is another important part of the plasma processes, because those radicals and diatomic radicals can lead later on to some agglomeration and some aggregates in your plasma while it cools down. But then there is also the fourth one, that is the radiation equilibrium. And this radiation equilibrium would be a problem in LIBS, and you can understand it. If you have a black body radiation, a black body, you have no radiation going out, because every photon emitted would be absorbed at the same time in this body. So what you want is you want to have a lot more processes for the ejection of those photons out of your plasma. You want emission more than you want absorption. And this is exactly what we want. We want everything governed by collisions, so as much as possible. So we want energies equilibrium by collisions. We want internal energies in equilibrium by collisions. We want those chemical reactions by collisions. And then we just want the photons to go out of this plasma and give us the diagnostics of the matter inside. And this is the very large notion that you can read in a lot of LIBS literature, the local thermodynamic equilibrium. Since you don't have the black body equilibrium, so the radiation equilibrium, you cannot have the thermodynamic equilibrium, but you can have it locally. That means that parts in your plasma, if you can divide it in different cells, can be in thermodynamic equilibrium. And this means you have three steps to know if you have a local thermodynamic equilibrium. You have to have domination of the collisional processes over the radiative processes. You need to have the different collisional processes to be in equilibrium one with another. So that means you want to have all the same temperatures. And then you want to have the diffusion and the relaxation shorter than the fluctuations of temperature and electronic density. That means you want to look at time scales where you can consider you have equilibrium and you're not only in transient phenomena. Why all this discussion on local thermodynamic equilibrium is because, as you saw in the slide before, you can address them with analytical solutions. You have the Maxwell solution, you have the Sa solution, and the Boltzmann solution. And all these solutions, you can use them to invert the signal you have from the LIBS to go back to quantification of the constituents of your plasma. And this is the key for a nice analysis with LIBS. So now we have all this notion. So we went through the extraction, so the sampling. We went to the excitation, and we went to the equilibrium of your plasma. Now you want it to emit, and you want it to be to cool down. So this is the next section, and this will be the last part of these processes. The LIBS, as we're saying, is just the LIBS is dynamic emission because it's a pulsed event, and it's not like you have in, for example, ICP or where you have a torch that can run for a very long time. No, here you have processes that can last just for microseconds or milliseconds. And so when you have the laser pulse that comes, can be a nanosecond time scale, then you have a very large continuum at the very beginning. This continuum we'll talk about it just after. Then you have recombination so of your electrons with ions. Then those ions, they become neutrals by recombination. And then those neutrals will become radicals by radical formation and association. So that means in LIBS, you will need to have a detection that can be gated, at least triggered with something that around 100 nanoseconds here, because you want to be able to address the right emitter in your event. So first, the continuum emission. Here is a very busy slide, but what I want to show is you have two kinds of contributions for this already for this continuum. You have branch-throwing emission, that is, instead of excitation of the free state like it was before by the laser, now those electrons have no energy left, so they want to cool down and they go to lower free states. And you can have recombination. That means they go on, so you have recombination of your ions, and then they go on bound states. And here you can see this expression on the top right is the ratio of what's the contribution of the free bound, so the recombination, over the free, that is the branch-throwing. And you can see in this reference there's a nice discussion on exactly how that works. And you can have branch-throwing at the very beginning, so that means you have first the free state transition, and then you have the recombination at very short later time. And here is a spectrum, and you can see when you have 20 nanoseconds, you can see that you have a very broad signal that then dies out and let the peak and the atomic transition appear. So usually in LIBS, you want to gate after this continuum, because this continuum doesn't provide you any information on the emitters themselves. It's more the electronic emission. Then you have this atomic emission, and this atomic emission, so people are very, very used with this one. And here is just an example of which can be a LIBS spectrum. So this one is just for iron, and it's between just on 15 nanometers. So 15 nanometers, you can have all those lines, and on the right you can see all the transitions possible in this iron atom. So you can see it's very rich, and so you need to have a very nice spectroscopic instrument to be able to reach a nice resolution and avoid any interference. But this atomic emission, so you have the browning, and so you still want to have a nice resolution, but this browning will be a big problem. So this browning is mainly due to three phenomena, as in many plasma spectroscopies. So you have the natural browning, but you won't be able to see it if you just have a normal spectrometer, or you have to have very high resolution. Then you have the Doppler browning, that is related to the temperature of your plasma. But a very important one is the collisional browning. It is related to the electronic density, And you can see an example on the right where you go from 200 nanoseconds to 1.5 microseconds. You can see that the width of the single line will just go down and will be lower and lower because your electronic density will be lower and lower in time. So this is a very important notion to have when you want to do fitting and quantitation of your spectrum. Then another big problem that can happen in LIBS is the self-absorption. So the self-absorption, what does that mean? It's just so you begin to be in the process like we're saying with the black body. So you have the photons are emitted by the excitation of the ions, but they are reabsorbed by another one. And this will happen mainly, you can see in the case A and C, that will happen when you have the excitation on the lower states, because the probability for absorption will be higher than the case B. But besides self-absorption, you can see that the case B here, it's not possible to fit it with a very nice void profile or a Lorentz profile. So what will be, what is disclosed? And it's because you can have, you have gradients in your plasma, and the LIBS plasma is not controlled. You have a LIBS plasma with temperature, electronic density gradients. That gives you asymmetry of your lines, like the case B. And if you take this into account, like it was done in this work, you can reproduce the asymmetry of lines and even the self-reversal of some lines. So that means you have to be careful when you do analysis with LIBS. It's just you have to look at regions where you really know what are the gradients, or you want to have the most homogeneous plasma as possible. Then the last emission I want to talk about is the radical emission. So this is mainly from diatomic radicals. Could be oxides, could be cyanides, and the diatomic carbon, for example. Those are mainly the well-known radicals you have in LIBS plasma over the several years. And here is an example of the CN transition. So this is in the visible. So those are transitions between electronic states, you can see on the right. And that will give you rotational and vibrational temperature to give you an idea of the equilibrium you are, because those are due to collisional processes as well. So you want to be able to address those issues. Then so we covered, I think, everything from the beginning. So sampling, excitation, expansion, collisional equilibrium, and then emission. So you have a broad idea. I didn't go so much in details, but you have a broad idea of what is the LIBS event and why it could be very difficult sometimes to address a specific problem. But besides that, you can see that so many parameters can give you a nice way to optimize the technique and optimize it for a specific problem. And now I want to conclude this talk with some niches for the LIBS, because sometimes, as we were saying at the beginning, LIBS could be the only option. And one example here is if you want to go in very hazardous environments and you don't want to have any contact, any human, any electronics sometimes, because here the example is hot cells, and because of radiation, you don't want your electronics to be to have the parasites of those radiation, and even you want it to stay operational. So an idea, as you can see on the left, is your laser just passed through a window, you analyze there, and your emission goes back for this window. And then you have the LIBS is the only option if you want to go in this kind of environment. Another one that is very well developed in the LIBS community is the standard detection of threats. LIBS is very good at detecting atomic composition. So if you want to detect chemical or biological threats, this is a very nice option if you want to go towards 100 meters, and it's been proven. And even explosive detection has been done and has been proven many times over 100 meters. Another kind is the production chain monitoring, because you have the nice opportunity to have high repetition rate lasers. So you want to follow each product on a chain. You'll be able to do it if you take lasers that could be kilohertz, for example, and you can analyze each of them in a single shot. And there is a large overview in the LIBS books that I mentioned at the beginning of this talk. Another trend is the space exploration. For sure, sometimes, like in this case, I really like this picture because you have some geometries that you cannot put any analytical technique there on this rock. That would be very difficult to access this point. So the laser is it's the best option, and LIBS is very well suited for that. Then I want to really conclude on this last slide with what I think is one of the future application of LIBS and development is the forensics, because in forensics you have so many samples you want to analyze. You want that with a single system. You don't want to have too much preparation because you need to go fast to provide the conclusions. So here is what we call the CSI effect. Is all the electronics and all the technology you can get in just a simple case. LIBS can fit in this kind of case with compact lasers, compact spectrometers, and just a small computer. And this is, I think, a very nice step towards the future for the LIBS application. So I want to thank you for attending this conference, and now I will let Dave be the speaker.
All right. Well, thanks a lot, Matthew. That was a great presentation. Before we get started on the question and answer session, I'd like to remind our audience how to submit questions for the live Q&A. As a reminder, text chat is located in the lower left-hand side of your screen. To submit a question, type your question in the small text box at the bottom, and when finished, click the Submit button. Please note that due to time constraints, our speaker may not be able to respond to all questions submitted. If we did not answer your question during the live event, you will receive an answer from our team. So let's move on. We have a question here from one viewer. It's a pretty short and sweet one. They would like to know, what is the depth of penetration?
So the depth of penetration usually can be in a couple of tens of nanometers to not even a micrometer. So it's very on surface. So it's just a small, I would say, imprint on your sample. Some people will call it damage. It's very, very simple. It depends on how precious will be your sample for you if you want to analyze it or not.
Okay. We have another viewer here who indicates that who would like to know what is the what is the difference between laser ablation OES and LIBS?
So there is no difference, I would say. The laser ablation, just when you say laser ablation OES, you don't include the fact that you have a plasma, but in the acronym. But this is exactly the same technique, I would say.
Okay. And we have another viewer who would like to know how was the calibration done in your presentation?
So the calibration is something very, very important, and then it really depends on the application you have. For example, if you go in the industry and you want to analyze metallic sample or an alloy, for example, and you know exactly what you have, and this is a very small set of samples you get, so you can get calibration samples, and for example from Denist or any other company, and then you just draw your calibration curves. Another next very interesting trend since '99 has been the calibration free. That means you use the notion of equilibrium that I was talking earlier, and because you can invert the signal thanks to those analytical relations, and so you just have this the spectrum itself you go back to the concentration. So it has shown some going to the ppm can be possible with this kind of calibration-free technique, and this is one thing that the whole community in LIBS is working on to provide this kind of very unique calibration-free analysis.
Okay. And we have two different viewers who ask similar questions. They would like you to comment on the quantitative capability of LIBS, and is it a quantitative technique?
So as soon as you have your calibration, you can go with the quantitation. Then, as I was saying, it really depends what you want to do. So you will be very careful with your calibration curves if you want to go very quantitative. Some people have mentioned in all the literature, you can go towards ppb. There is no problem for many techniques, but then you optimize your plasma for just these elements, for example. If you want to have a broad image, and you can have, like in the biological application or food application, if you have, you can have like 20 elements emitting at the same time. And the thing is, you have to deal with the continuum. Then you can reach even like ppm for sure, but then several techniques have been developed to address single elements in LIBS and provide sub-ppm and towards ppb.
Okay. We do have another viewer here who would like to know, what is your opinion on extending LIBS to longer IR wavelengths?
You mean with the laser or with the detection?
I believe the laser.
Okay. The IR region is very nice in a sense of the eye-safe concerns. As you know, the safety is better. So sure, you still need enough power to create a plasma. Some people will say it's eye-safer, more than eye-safe. But this is one thing that the IR can be great. Another thing is, and then we go back to the sampling question, is if you want to analyze polymers or molecular samples, then you have vibrational absorption there that can be very addressed well if you have tunable lasers in the IR, and that can lead. There are some publications on this idea, and having ablation with mid-IR lasers for addressing some bonds and enhance the signal of some elements you want to address.
Okay. We have another viewer here who would like to know, how much is the typical pulse energy used in LIBS?
I would say you can stay on few millijoules to few tenths of millijoules. It can change, but this is the order. Yeah.
Okay. We have another viewer here who would like to know, let me just get to it here. One of they're saying that one of the LIBS limitations is its low sensitivity. What strategies can help to overcome that?
So yeah, as we were saying, so then you don't go with single pulses, and then you can address it with different techniques, like adding several pulses. And for example, there's the double pulse itself is you can keep on the plasma going for a longer time. You add there is one that is if you just want to go very low in detection and not in quantitation, you can have the microwave LIBS is something that can be used, and we explored in our lab. One thing also is to use resonant. You can do fluorescence in your plasma, so you address a specific atom or specific element, and you can. There are some new work done in Canada, and they were doing the ablation and this excitation of single element by a single pulse. So if you want to go in very good limit of detection, then usually you want to adapt the technique. So you just use LIBS as a plasma creation just for creation of the plasma. And then you use another pulse, and you can do LIBS. You can do different other techniques, optical techniques, I would say, to go lower in detection.
Okay. We have another viewer here who mentions you spoke of parts per million analyses. Can LIBS do major element analyses of inorganics?
That's one thing. It depends what's your what's the need you want in the percentage of error. But you can go to a few percent for sure when you have 99% elements. I haven't worked so much in this field, but you can go to lower than 1%, I'm sure.
Okay. We have a viewer here with kind of a general question. What are the biggest challenges currently faced by the LIBS community?
One thing was in the abstract, I would say, is the recognition by the field. But I hope that this presentation can help to have an idea of what we are capable of. But another one is really to deal with this low limit of detection just with one pulse, for example, having protocols to achieve analysis in labs, I would say more often. And one big trend is really the development of the calibration for LIBS, and I think this is one big step to go forward.
Okay. We have another viewer who would like to know, is wavelength interaction a problem for LIBS? For example, the big sodium band, which you have with ICP-OES.
Like those lines, if I understood the question, so if you want to talk about the interference, I guess, you can get in your spectra, or in this case, you can always find out where you want to go in your spectrum. But for the wavelength interaction, I think it's just you can adapt either the spectral region or the laser interaction if you want to get rid of this. This is not an issue.
Okay. And we have a viewer here who would like to know which laser do you recommend, UV, IR, for example, for each kind of sample, metal, semiconductor, isolant?
That's a tough question. As I was saying, so we are several people working. Is it possible to have protocols? And this is a study that we need to go. We need to extend. I would say it depends what you want to do, and I mean that could be the answer to a lot of questions in LIBS. But this is like the magic of LIBS. It's just you can optimize it. So and for metals, as you say, you want to have a low reflection, so you want to go with lower wavelengths. So I would say visible UV. Then if you have semiconductors, for sure you want to go with, as we're saying, saying in these slides, you want to have a large absorption, but you want to have a low reflection. So you can be a bit off of your band gap to work on this. Then for organics, as we're saying, it's very interesting to look at UV, for example, to address the absorption bands, or you can go in the IR to address very specific vibrational bands.
All right. Well, I think that's about all we have time for right now, but thanks again for being with us, Matthew. We have a lot of questions for you. Yeah, we'll be sure to get you these questions that are left over because there's a big list.
Okay.
All right. I'd also like to thank the audience for their interesting questions and participation in today's event. And I'd like to thank Andor Technology for making today's educational webcast possible. Please note that this webcast will be available for on-demand viewing through September 29th, 2011. You'll receive an email from Spectroscopy alerting you when this webcast will be available for replay. Please invite your colleagues who may have missed this live event to view the on-demand by forwarding them the announcement. On behalf of Spectroscopy, I'd like to thank you once again for attending today's webcast, Basic Principles of Laser Induced Breakdown Spectroscopy. See you next time. Goodbye.